Example 3, we can see, and I was going to check this. X goes from 0 to 3, and y is a function of x. So we're good. We don't have to worry about anything here. We can easily draw this picture. That's one of those functions in your red packet. We know that x to the 3/2 looks like this. Okay, and then so from 0 to 3, 1, 2, 3, we're finding the length of that arc. Okay, length of that arc. Now, let's do a little estimation here to start off with. 3 to the 3/2, 3 to the 1/2, so I don't know, somewhere near 5, let's say, somewhere close to 5, a little bit more than 5. And then let's estimate, just using the Pythagorean theorem, 3 and 5. Okay, so somewhere around 6. Okay, so somewhere around 6, maybe a little less than 6. So we get from there to there, a little less than 6. And so our curve needs to be a little bit more than 6 possibly, or right around 6. So let's see how it goes. All right, so the length of the arc. So again, we need to make sure we remember our formula. The length of our arc would be the square root of, the integral from 0 to 3 of the square root of 1 plus dy dx squared dx. So let's make sure we get that. Okay, good. All right, well, let's find our dy dx. We can write y prime if we want. Would be 3/2 times x to the 1/2. And again, we're going to go ahead and square the left side. We're going to square the right side because that's ultimately what we want. So we get dy dx squared is 3/2 squared is 9/4, and x to the 1/2 squared, so square root of x squared is the absolute value of x. But again, x is between 0 and 3, and so the absolute value of x, the absolute value of bars don't help us any. So we're going to write this as 9/4 x. So that's our magic term that we need to go ahead and put inside of the radical. So now we can calculate the length. So 0 to 3, integral from 0 to 3, 1 plus 9/4 x dx. So in looking at that integrand, there's no formula for that, so let's run through the series of steps here, series of methods that we've learned. Formula, u sub parts. That's certainly not parts. It's certainly not a formula. So we have to do u sub. So let's let the u equal 1 plus 9/4 x du 9/4 dx. Now we don't have a 9/4 out there, so we just have a dx that we need to get rid of. This is going to be our u. Isn't this great? We get to practice the stuff we've learned, and you actually have to still remember that stuff you learned a while ago. I think it's fantastic. So we're going to go ahead and multiply both sides by 4/9, and we're going to substitute in 4/9 du for our dx. So that's going to be what we put right there. The u goes right there, and everybody's happy. So we go, now let's not forget, when we're dealing with a definite integral, we've got these limits of integration that are defined in terms of x. Well, let's define them in terms of u, and let's do that over here so we can get this stuff out of the way. We want to find u of 3, and this might open up a big can of worms. So if we put a 3 in for x, we get 27 over 4. That's not favorable. 27 over 4 plus 1, well, that's 27 plus 4. 27 over 4 plus 4 over 4 is 31 over 4. Not really happy about that too much, but if we put a 0 in for x, that one makes me happy. So we're going to go u of 0. We're going to try this. If we want to try it a different way later, we can if we run into trouble. So u of 0 is 1. U of 3 is 31 over 4. And then we have our square root of u, right? Square root of u du. But I'm going to write that as, instead of square root, I'm going to write u to the 1/2 du. So this is not bad now. We made our nice little substitution. We can easily come up with the antiderivative of u to the 1/2. And the antiderivative of u to the 1/2 is u to the 3/2. I think we did that up above there. Divide by 3/2 or multiply by 2/3.